Hi everyone. My name is Usha Pant and I am a recent graduate from Idaho State University. My research was on modular structural concrete insulated panel, the testing of it. Even though the use of precast structural concrete insulated panels in construction can offer structurally sound buildings, structural engineers rarely consider it as an alternative to wood or masonry methods. These are the methods that are very popular due to a lack of understanding of the material and construction technique. So it's what are SCIPs? SCIPs are the version of structural insulated. All right, SCIP panels are a version of structurally insulated panels. It uses reinforced concrete instead of plywood. That's used in structurally insulated panels that are made up of wood, and they provide two load-bearing faces. And the one that I'm going to talk about is Metroc SCIP. It's a modular form of SCIP. It's a type of SCIP panel. SCIP panel basically looks like the figure that's shown there. It has a foam in between the two surfaces with mesh, and then on the top of it there's like a concrete layer. The advantages of SCIPs are it provides good thermal insulation. It increases the thermal resistance of built structure because it's made up of concrete. Time efficient, it's very time efficient because it can also be created there are type of SCIPs that are precast, or so it can be created inside the created and then transferred to the construction site. It's energy efficient because there is significant reduction in energy consumption for heating and cooling, and also it's environmentally friendly because uh, there's reduction in the environmental effect of a construction project on a construction site. So modular SCIPs. So modular SCIP, as I already said, is a type of SCIP. They are built. The only difference is that they are built away from the construction site and then transported for installation. They are fabricated and assembled using a portable hydraulic jig press and pneumatic hog rig tie, and also appropriate connection details and for the wall foundation and wall slab are identified for the on-site assembly. So it's showing how it's transferred and then uh, how it's connected in this construction site. So my presentation, my research was on the experiment of the Metroc SCIPs. It was a shear failure experiment that was done in two large SCIP panel. So the consolidating concrete that was designed was using this volume and weight. We used cement, fly ash, fine aggregates, coarse aggregates, water. That's used for most of the concrete panels. So the experimental investigation that was conducted in Idaho State University Structural Lab. The two SCIP panels were developed, manufactured, and evaluated according to the ASTM standards. So this picture shows the pouring of the concrete layer. It's pouring the bottom layer for the concrete panel, the SCIP panels. So this one with the form with the truss on the outside is the um, it's gonna act inside the concrete layer. So on the top of it, first the bottom layer was poured, and then the foam covered with the truss was kept, and then on the top of it 1 inch concrete layer was poured again. So the total concrete layer thickness was of 2 inches. This is how it looked after pouring, and then So for finishing the top, we tried to minimize. We tried to make the top layer as fine as possible. So to minimize like air bubbles, and also after it was made, it was covered with wet burlap for 7 days, and then again kept for like 28 days, and was like the water was provided almost every day. So after the after making the panel, 6 cylinders were made to for testing the compressive strength of the concrete at 7 days and at 28 days. So for the testing of the Matroc SCIP, for the shear failure test of Matroc SCIP, so this is how the test was conducted. So both the panels were about 4 by 5 feet tall and wide. Each panel were like simply supported and in between two rollers and was loaded using load cell. And also the point load was applied at 12 and 13 inches respectively. So almost 12 inches. So this is how the test looked during in the structural lab on the test day. So there is the specimen here. So the load cell, it provided the load. Hydraulic ram, uh, it load cell transferred the load information to the computer so that we could see the value, and the spreader beam was used to provide like the load um, for the specimen. The spreader beam was about 4 feet wide. That's like it was almost the size of the specimen, and there below it there's like a roller support which was hold strongly, and also the two string pots were also used to measure like we also wanted to measure deflection for it was for my thesis, so we also wanted to measure deflection. So two string pots were kept on each side of the panel. So one was kept at the end, around the end of the spreader beam, like where the loading was applied, and the other string pot was applied at the center of the beam from the support, so about 2 feet distance. So this is how the string pots were kept, and so this is the end support details that I already told. So spreader beam, and then there was a 0.5-inch roller support, and below that there was I-beam support of 5.6 feet. So below the spreader beam there was a 2-inch rolling plate to minimize the friction, and also so that it doesn't move. So after the test, we observed many shear cracks. It's on. We observed many shear cracks on both panels. So this is the shear cracks before and after the testing for the panel 1. That was we measured the amount of like force when the crack was more than 0.1 millimeter. So after the testing was done, the concrete panel was like hammered to see if there was any buckling or not, and we found that there was buckling on both panels. So buckling also played a huge role in determining like the shear capacity of the panel. So this is the shear cracks for before and after test for panel 2, and also there was buckling. So what were the experimental observations were that the yield capacity and the ultimate load capacity for panel 1, both panel were around 20,000 pounds, so around 20 kips, and yield capacity was around 3 kips for panel 1, and for around 5 kips for panel 2. So we can see that the yield capacity, the ultimate load capacity for panel 1 and panel 2 is almost similar, around 20 kips. So there was not much difference. So one of the important part of my thesis was to determine uh, determine the shear capacity. So to compare the shear capacity from the experimental testing, and then also use analytical method to compare and see if the values were uh, matching or not, if the testing is valid or not. So but I have not included much of my testing here because it was for my thesis and it was much more in detail. So this was how the testing was done for the large scale SCIP panel for the shear failure test. So in the conclusion, what we found out that was that the average effective movement capacity for the METROC panels, that it decreased until a certain point. So in this case, after 16 feet, the average up until 16 feet, the average effective movement capacity decreased, and after that, it somewhat remained constant. And also the maximum deflect. We also measured the maximum deflection of both panel. So the maximum deflection was assumed to be on the point where load was applied, and also there was buckling of diagonal bars, and also we sorry. So these were the references that I used for the testing. So that's all. Thank you.
Very good. Thank you, Usha, for your presentation. So we have time for a couple of questions. So first I ask from the present audience if they have questions. Please just go over to the microphone so you all can hear your question, if there is. Or if you have any questions from the virtual audience. All right. But I have a question. So, okay. Usha, would you please tell me that what do you think if we increase the size of that diagonal bar and we have a better connection of that bar to the top surface of the panel, do you think it's just going to increase your shear strength? Because it looks to me that was a structure's weak spot that started to collapse around that. I just saw some web cracks happens because of that buckling. So if you think we increase the size of that diagonal bar, it's just going to be any different in the shear strength?
I think so. While I was calculating the shear capacity, I used I assumed the diagonal bars to be like a triangle. But I think yes, if I increase the diameter and the height of the diagonal bar, the width and the height of the diagonal bars, I think it would increase the shear cap. It would make it much more stronger.
Excellent. Very good. And I think the same. I think the same. That would be changing the shear strength because it's going to change the failure mode probably.
Okay, which manufacturer you use for this particular experiment?
Which manufacturer?
The panel. Who made this panel?
Oh, so actually this panel was made by one of the graduate student who graduated before me. So he had a panel not the complete concrete panel, but he had the panel with foam around with the trusses outside of it, and I just used it I just made it like concrete panel. I just poured concrete on both sides and then on every side 1 inch concrete layer. So this was made by one of the graduate student.
For your information, we finished a 5 building with the insulated panel in the North Carolina pharmaceutical facility, and we just finished it, with the 52 feet high panel. It's kind of similar structure.
Same structure.
Same structure,
right.
Yeah.
Interesting.
Interesting, yes.
Thank you. Thank you all.